You might have seen the power of heat vision in films, TV, or video games. But did you know we can unlock this incredible ability using the science of infrared? Infrared is one of the 7 distinct groups of radiation on the electromagnetic spectrum, where waves in the electrical and magnetic fields carry energy at the speed of light. The electromagnetic spectrum ranges from long, low energy waves called radio waves, all the way up to short wavelength, high energy gamma rays. Visible light is also on this spectrum, with each colour having a corresponding wavelength. Blue-violet as the shortest wavelength and red as the longest. As for wavelengths longer than red, we have the group infrared. Infrared radiation, also known as IR, is emitted from every object in the universe and is also known as thermal energy or heat. Objects with low thermal energy don't emit much infrared and will feel cold, whereas objects with high thermal energy will emit much more infrared and therefore feel hot. In heat vision, also known as thermal imaging or infrared thermography, detectors measure how much IR is received from a particular area and match this to a temperature. We represent temperature with colour to help us visualise this better and to help us identify otherwise invisible cold and hot spots. How can we use infrared to our advantage? Infrared cameras can see heat-emitting objects even within situations where visible light is insufficient, such as at night or when obscured by smoke. Warm-blooded creatures like us humans are easily distinguished from their cold environment, making infrared useful in hunting, search and rescue operations, and wildlife cameras. Thermal imaging is worlds apart from using a simple thermometer or a heat probe. It sees these infrared waves like we see light and can detail a complex image. Infrared imaging can be used to test a person or animal's temperature from a safe distance, or tell firefighters when an unseen heat source creates hazards. Thermometers aren't entirely useless though. Classic glass thermometers are cheap, and thermal imaging can only capture the surface temperature, not the temperature on the inside of objects. Infrared is also used all over our homes. As we've said before, it's heat. By putting energy into an object, we can cause it to emit lots of infrared radiation. For example, if we put an electric current in our grill, the heating element will warm our food. Similar types of these get used to keep ourselves warm with electric heaters, or even get used in our games consoles. Some entertainment systems use infrared LEDs to create a sensor bar, where an infrared sensor at the tip of a controller can determine the direction in which it is pointing. In fact, you could get rid of that sensor bar and replace it with 2 lit candles. The infrared emitted by the flame would work just as well. Even some animals have evolved to use infrared, with mosquitoes, vampire bats, some snake and beetle species, and bedbugs using partial infrared vision to find their food. Did you know infrared has uses beyond our planet, within astronomy? Scientists observe the universe using infrared to detect waves emitted by cooler planets, stars, and nebulae, objects that are otherwise too dim to be seen by visible light. Planets outside our solar system, known as exoplanets, can be difficult to spot, as their star will glow millions of times brighter than whatever light an exoplanet could reflect on its own, a difference that makes the exoplanet almost impossible to detect. But in infrared, we look at heat, and a host star may only be hundreds of times hotter on the surface than a closely orbiting exoplanet. These are temperatures close enough that we can spot it. But what else can we spot in the cosmos with infrared? Well, visible light has a short wavelength. These means that they are scattered and absorbed easily by dense clouds of gas and dust found in space, sometimes known as nebulae, not unlike trying to look outside on a foggy morning. Using the longer wavelengths of infrared, we can look through these fog-like nebulae as longer wavelengths are less scattered, revealing the heat from the celestial bodies behind it. These nebulae are often the leftovers of cosmic events like star formation and star death, so being able to see behind the curtain, to see the bright glow of a newborn star or the remains of one, like a white dwarf or even a neutron star, can help us piece together and research the lifespan of stars across the universe. We can also spot distant galaxies whose visible light waves have been stretched into infrared by the expansion of the universe, like the rubber skin of a balloon as it's being inflated. You might have heard this as redshift. These distant galaxies can help us learn more about the formation of the early universe, as the huge distance means that the light can be billions of years old. Did you know that you can use infrared to work out what objects are made of? To explain this, we need to understand what's happening on an atomic scale. Imagine a water molecule, H2O. The two hydrogen atoms are bonded to a central oxygen atom, as if connected by a spring. When exactly the right wavelength of infrared hits the molecule, the atoms absorb the energy. This makes them wobble, and the bond between them stretches and contracts like a bouncing spring. Molecules like methane or carbon dioxide also have wavelengths that make their atoms wobble, but each wobble wavelength is different for different molecules. So what if we have a mystery material? Well, we could fire a range of infrared wavelengths, or a spectrum of infrared, at the object. Some of them would be the exact wobble wavelength for a particular bond. Only these wavelengths will be absorbed by the object. We already know which bonds they might match up to, so we can put all of this information together and work out exactly what the mystery material is made of. This is a process called spectroscopy. Spectro, referring to the electromagnetic spectrum, and scopy, to examine. We examine the electromagnetic spectrum to learn more about what atoms a molecule will be made of. What we described above is actually called absorption spectroscopy. We pass a spectrum through an object and look at this on the other side to see what's been absorbed. But what if these objects are really far away, in space? Let's say we want to learn about the composition of a nebula. If this nebula has a star behind it, we're in luck. Stars produce light right across the EM spectrum. As the star's light passes through a nebula, the wobble wavelength for the different atoms inside it will be absorbed. So when we see this light, the infrared part of this spectrum from the star will be missing just those particular wobble wavelengths. Like we explained before, we can work out what these atoms must be, and therefore what chemical elements the nebulae is made of. The elements are potentially the building blocks for a whole new solar system.